Hi, this is lecture 21 of Engineering Physics 1. Today we will continue studying fluids, but unlike lecture 20, where our fluids were kind of stationary, so we had those fluids, they didn't move, we would submerge something into them, but there was no motion, overall motion of the fluid. In this lecture, we will see what happens when the fluid moves. So I want to start by saying that the motion of a fluid is, in general, a very difficult problem to solve. Since fluids don't conserve their shape, different parts of the fluid can move independently, and this could lead to a very complicated motion. This is called a turbulent motion, where different parts of the fluid are moving kind of randomly. I'm sure you've seen pictures of turbulence. And turbulence is, as of now, not a completely solved problem in physics. So to make things simpler, what we will do is we will only consider laminar flows. Laminar flows, unlike turbulent flows, are the flows of fluid where you have these streams and where you have two parts of the fluid close to each other. They will remain close to each other as they move. Unlike turbulent motion, in which these two parts of the fluid could be close in the beginning, but then because of the random motion, they could get really far away from each other. On my lecture slides, on slide 2, I have I show two cases of two sets of laminar and turbulent motions. Hopefully that gives you an idea of what I'm talking about. But this is not enough. We will simplify things even further. And what we will do is we will only consider fluids as they flow through some sort of a pipe. And this pipe will keep them in a constrained part of space. So they're not going to be completely free to move. We will also ignore viscosity. Viscosity is a description of how quote-unquote sticky the liquid is. So for example, if you have a realistic liquid and it moves through a pipe, the velocity of the liquid will be higher in the middle of the pipe, and it will be lower at the edges of the pipe, because as you get closer to the edges, there is this effective friction with the walls that reduces velocity. But we will ignore that effect, and we will assume that when liquid flows through the pipes, there is no viscosity. And if I take a section of the pipe, then all points in this section move with the same velocity. So this is another simplifying assumption that we will make to make our job of studying moving liquids simpler. Now what we will do is we will look at some laws that govern motion of the liquid. So the liquid itself, as it moves, is of course made of small particles, small molecules, and those molecules obey the laws of physics that we have studied. They will experience forces, and they will move under forces. But when we study fluids, we usually don't want to go to that level, to the level of individual particles, because that would make things way too complicated. So we will study fluid as a whole, and we will formulate new integral laws that govern the motion of fluid as a whole. So now I will move to slide number 3. The first major law of liquid flow that we will consider is the what I call the conservation of volume. So conservation of volume, I think, is pretty simple to understand. we know that if we have liquids like water, they could change their shape, but it's very difficult to make them change their volume. And so if I have a pipe, and if this pipe is full of water, as opposed to half full, let's say it's full of water, and if the water is flowing in this pipe, then the amount of water that goes through this section, section A, in unit time, let's say in 1 second, has to be equal to the amount of water that goes through the second section, section B, in the same amount of time, 1 second. And this is just how it has to be. There is no other way if the volume is conserved. If you think about it, this law is easy to understand. Let's say if we had more liquid going through section A, and if we had less liquid going through section B in the same time, then there must have been some sort of collection of liquid in between. And since the pipe is full, the liquid cannot collect there, because that would imply that the liquid is being squeezed and it becomes denser and its volume goes down. So since that's not possible, all the liquid that goes through in 1 second through A must also go through B after some time, also in 1 second. So this is kind of obvious for a pipe that doesn't change its size, but it has some implications for fluid flow for pipes that change their sizes. So one picture that I have on my slide number 3 is this pipe that starts out as a wide pipe, and then it narrows, and on the other end, it's a much narrower pipe. Now, what I want you to do is I want you to think about conservation of volume. And I want you to think about what happens as your pipe narrows. So I have some amount of liquid going through this wide section. Let me call it A1 in let's say 1 second. And then I must have the same amount of liquid go through the second section, section A2, in the same amount of time, in 1 second. So if you look at this drawing, then you will see that if this is the volume of water that I need to pass through A1 in 1 second, since A2 is narrower, and since exactly the same volume has to go through A2, if I draw the same volume over here, this volume it will have less cross section, but it will be longer. So a longer stream of water goes through A2 compared to A1. And the length of the stream of water that goes through the section is almost by definition velocity of this water, of this fluid. So my conclusion from here is that water must flow faster in section A2 compared to A1. So faster here and slower here. And this follows again from the fact that liquid cannot be compressed, and you have to have the same overall amount of liquid going through all sections at all times. Now, if you write this mathematically, the volume of this section of water is its cross section times this length, and in the same amount of time, you will have this much volume going through A2. So that's A2 times L2, and I will divide it by the same amount of time. So the length, quote unquote, of the liquid stream going through divided by time is velocity. So from here it follows that if I have an incompressible fluid, and if it goes to a pipe that changes its cross-section, then at all points in this pipe, I have its cross-section times velocity equal to the second cross-section times velocity. Or in other words, where the pipe is narrower, you have a faster flow because this A times V is something that's conserved along the streamline. So now I will move to slide number 4. On slide number 4, I show a couple of cases of this continuity of volume. So let me write this equation here so that we have it for reference. A1 times V1 equals to A2 times V2. And so one example is the top right figure where you have water flowing. So you have this water flowing, and the question is, and you can observe it at home, this water stream is kind of narrowing down as it falls. So you have much higher cross-section here and a much lower cross-section here. And why this happens kind of can be explained by this continuity of volume, why this has to happen. As your water drops, it gains velocity, so it moves faster here and it moves slower here at the top. And since it's kind of the same stream of water, even though it's not in a pipe, the cross-section times velocity has to be the same. So where you have low volume, you have a high cross-section, and where you have high cross-section, you have low velocity. So not volume, velocity. There is also a picture of a pipe on the bottom right corner. That pipe kind of looks like this. It starts with a wide section with a radius of 2r, followed by narrower section of the radius r, followed by even wider section of radius 3r. The question is, in which section does the water flow the fastest and the slowest? And if you remember what we just said, if you look at this formula, hopefully this question is very simple. The answer to this question is that the water has to flow the fastest in this region where the pipe is the narrowest, and it flows the slowest in this region where the pipe is the widest. Now, in your homework 21, you have a couple of exercises in which you have to apply this this concept of the continuity of volume, or conservation of volume. I think you have a few cases where you have a stream of water, and the stream is divided into 2 parts or many parts. And then you have a reversed case where you have several streams of water combined into one stream. And we also have a picture of this in the bottom left figure of slide number 4. And so it's the same idea here. Basically, every time you have the situation where the stream divides or is combined, the only difference is that now when you take a section, you have to consider both arms of the stream. So if the water flows in this direction from left to right, then the amount of water flowing in this section A1 must be equal to the amount of water flowing in sections 2 and 3 combined. And in this case, since it's a stream 1 that divides into stream 2 and stream 3, the way you would write your continuity equation is the following. You would write A1 times V1, this is kind of the amount of water that goes through this section in unit time, is equal to A2 V2 plus A3 V3. So the amount of liquid that goes through section 1 is equal to the amount of liquid that goes through sections 2 and 3 combined in unit time. Now, what I want to do is I want to solve a sample problem from the textbook that has to do with this conservation of volume. This is problem number 84 from your textbook. And in this problem, they explain to you how coughing works. This is slide 5. And basically, they tell you that you breathe in a large amount of air, you trap it, and you increase the air pressure by contracting the lungs. And then by suddenly reopening your glottis, you you make this stream of air move very fast, move out very fast. And so the numbers are, the flow rate is 7 10 to the minus 3 cubic meters per second. That's how much air is expelled from your lungs per second when you cough. And there are two questions. The first question is, they're actually similar questions. The questions are, what's the airspeed through your trachea as you cough for the two cases? In case A, the diameter is 14 millimeters. This is kind of an average size of trachea. And then they ask you, what would the speed be if instead it contracted to 5.2 millimeters? So 5.2 millimeters here. So before I start solving this problem, I want to start by thinking about what do I expect before I start crunching numbers. What kind of numbers do I expect? So I need to find my speed here, and then I have to find my speed here. And so if you think about this, my expectation is that since I have a wider pipe here for the air to go through, and I have a narrower pipe here for the air to go through, I would expect this number, let me call this velocity B, to be higher than velocity A. So when I solve this problem, I will look at the numbers, and if VB is more than VA, I'm happy. If it's not the case, then I will go back and look for a mistake. So why don't you pause this video, think about this, and then play the video again and check your solution with mine. Okay, so let's now compute the numbers. So let's start from case A. I have this pipe which has a cylindrical shape. They tell me that the diameter is 14 millimeters. I will convert it to meters. So 14 millimeters is milli is 10 to the minus 3. So this is 0.014 meters. And since this cross-sectional area is a circle with a diameter d, which is this much, my area is pi r squared. And since r is half of the diameter, it's pi diameter squared divided by 4. So I get pi 3.14 divided by 4 times 0.014 meters squared. So I don't know the velocity. Velocity is unknown, VA, but I know that the total flow is 7 10 to the minus 3 meter cubes per second. So 0.007. And from here, my VA is equal to 4 times 0.007 divided by 3.14 divided by 0.014 squared. So for part B, I will do exactly the same thing. There is no point in going through these steps. My VB will be equal to 4 times 0.007, but I will divide it by 3.14 times. I have a new diameter now, for 5.2 millimeters, which is 0.052 meters, 0.052 squared. Now I will compute these numbers and I will compare them and I will see if my expectation is met. So I computed those numbers and here I got about 45 meters per second. And here I got 313 meters per second, which is very close to the speed of sound. And so you see how big of a difference this makes. And that's because our radius is squared, our diameter is squared. You go from 45 to 330. And these numbers worked out exactly as expected. Velocity in case B is higher than velocity in case A. Okay, so this is first half of our lecture 21. There will be a separate video for part 2. In the first half, we talked about the conservation of volume. And in the second half, we'll talk about the second important law that governs the fluid flow, which is the Bernoulli law, the Bernoulli equation.